Hello everyone! Today, we'll study generic attacks for finding preimages and collisions for a hash function. We'll spend some time analyzing the Van Oorschot-Wiener algorithm for finding collisions. This algorithm has minimal storage requirements and can be effectively parallelized.
A generic attack on a hash function does not exploit any specific properties the hash function might have. So from the attacker's perspective, the hash function is viewed as a black box to which the attacker can present any message of her choice, and the black box returns the hash of the message. When we analyze generic attacks on hash functions, we view the hash function as a randomly selected function in the sense that for each message x in the domain of the function, we assume that the hash of that message was chosen uniformly at random from the codomain of the function. From a security point of view, a random function is an ideal hash function. However, random functions are not suitable in practice because they can't be compactly stored. The only way you can describe a randomly selected hash function is by a giant table, which for each message in the domain gives the corresponding hash value. Even though randomly selected hash functions aren't practical, we still assume that a hash function is a random function when we analyze generic attacks on hash functions. Here is a generic attack for finding preimages for an n-bit hash function h. Given a randomly selected hash value y, we'll repeatedly select arbitrary messages x and hash x until we find that h of x equals y.
For each message x, the probability that h of x equals the given y is 1 over 2 to the n, because the total number of hash values is 2 to the power n, and we're assuming that h is a randomly selected function.
Hence, the expected number of hash operations in the attack is 2 to the n. Thus, to ensure that the attack is infeasible in practice, we need to select n to be at least 128. If we do this, then the generic attack takes at least 2 to the 128 operations, which is our lower bound of infeasibility in this course. It's been proven that this generic attack for finding preimages is optimal. But of course, faster preimage finding attacks might exist that exploit specific properties of a particular hash function. Here is a generic attack for finding collisions for an n-bit hash function. We'll select arbitrary messages x and store the hash of x and the message x in a table sorted by first entry. We'll continue doing this until a collision is found. In other words, when we find a message whose hash is already in the table. Since we're modeling h as a random function, when we select arbitrary messages x, the hash values x are uniform at random. And so, since there are 2 to the n possible hash values, by the birthday paradox, the expected number of hash operations in this generic attack is roughly the square root of 2 to the n. To ensure that the attack is infeasible, n should be at least 256, because then the running time of the generic attack is at least 2 to the 128.
It's been proven that the running time of the generic attack for finding collisions is optimal. However, a major drawback of this generic collision finding algorithm is the space required, which is roughly the square root of 2 to the power n. The size of each table entry is n bits for the hash value, and I'll say n bits for the message x. So the size of the table is roughly the square root of 2 to the power n times 2 n bits.
If n is 128, then the expected running time of the generic attack for finding collisions is 2 to the 64, which is considered feasible. However, the expected space required is roughly 500 million terabytes. Recall that 1,000,000 terabytes is 1 exabyte, and so the expected storage for the attack is 500 exabytes. It was estimated a few years ago that Google had a couple of dozen exabytes in its backend. And so 500 exabytes would be too expensive even for Google. Thus, even though the running time of the generic attack for finding collisions for a 128-bit hash function is feasible, the space required for the attack is infeasible. We'll next study a generic collision finding algorithm due to Paul van Oorschot and Michael Wiener from 1993. The expected running time of the VW attack is the same as a previous generic attack, namely the square root of 2 to the n hash operations. However, the expected space required for the VW attack is negligible. Moreover, the attack is very easy to parallelize, and so if you had m processors available, you would get an m-fold speedup in the running time. I should mention that the VW attack finds a random pair of n-bit messages with the same hash value. It might appear that such a collision is useless in practice. However, the VW attack can be easily modified to find so-called meaningful collisions. I won't provide the details in this lecture, but you can find them in the optional reading section on the course webpage. So to conclude, if collision resistance is desired, then one should use an n-bit hash function with n at least 256. I'll next describe the VW parallel collision search method. The problem is to find the collision for an n-bit hash function. In the analysis, I'll assume that h is a random function, which means that for every message x in the domain, we'll assume that h of x was selected at random. Let capital N denote the total number of hash values. We'll define a sequence xi of n-bit strings as follows. The first term in the sequence, x0, is selected at random from the set of hash values. Subsequent terms xi, where I is at least 1, are obtained by hashing the previous term. The diagram on the right shows the sequence. x0 is the first term in the sequence, x1 is a hash of x0, x2 is a hash of x1, and so on. Now, the terms of the sequence cannot be distinct forever. This is because the terms are drawn from a finite set, and so the sequence must eventually collide with itself. This happens when some term xj equals a previous term xi. Once this collision occurs, the sequence repeats forever and ever. Let j be the smallest index for which xj equals xi for some I less than j. As I noted, such a j must exist since the terms xi are drawn from a finite set. Then, xj plus l equals xi plus l for all positive integers l. Now, since the terms of the sequence are drawn at random from a set of size n, by the birthday paradox, we expect the sequence to repeat after square root of n draws. And so the expected value of j is the square root of n. In fact, it can be proven that the expected value of I being the length of the tail of the sequence, is 1/2 the square root of n. And the expected value of j minus I being the length of the cycle, is also 1/2 the square root of n. To see why this might be true, consider when the sequence is about to collide with itself, namely when xj equals xi for some I less than j. Then, the index I can be any one of the values between 0 and j minus 1. So on average, you would expect I to be roughly half of j. And so the expected value of I is roughly half the expected value of j. Now, with overwhelming probability, I is non-zero, which means that with overwhelming probability, this row-shaped figure is not a trivial cycle. In this event, the terms xi minus 1 and xj minus 1 are two different hash values, which both hash to the same values, namely xi and xj. And so the pair of red dots is a collision for h, and this is a collision that we seek. One way to find this collision is to compute the terms x0, x1, x2, and so on, and store them in a table. However, the table would be too large, namely of size roughly the square root of n. The main contribution of Van Oorschot and Wiener was a method for finding the collision xi minus 1, xj minus 1 without using much storage. Van Oorschot and Wiener's idea was to only store so-called distinguished points. So, we'll select an easily testable distinguishing property for elements of the codomain of the hash function. For example, we might declare a hash value to be distinguished if its leading 32 bits are all 0. Let theta be the proportion of hash values that are distinguished. For instance, if the distinguishing criterion was that the leading 32 bits are all 0, then theta would be 1 over 2 to the 32. In a nutshell, then, the VW algorithm is to compute the terms of the sequence one at a time, but only store the points in the sequence that are distinguished. Here are the details. We begin by storing the first point x0 in the table. We then hash x0 to get x1, hash x1 to get x2, and so on. As we compute terms of the sequence, we only store the terms that are distinguished. These are shown by the blue dots. When a collision eventually occurs, we likely won't detect that it has occurred because we've only stored the blue points and not the black ones. However, since the cycle repeats after a collision has occurred, we will shortly thereafter encounter a distinguished point which is already in the table. We then will have detected that a collision has occurred. Let's define XA to be the last distinguished point before the sequence enters the cycle. Define XB to be the first distinguished point after the sequence has entered the cycle. Define XC to be the last distinguished point in the cycle before the sequence repeats. Then, the collision is detected when the distinguished point XD is computed, and it is discovered that XD is already in the table. It was stored when XB was computed. The next task is to find the collision, which are the red points in the diagram. I've expanded the green portion of the diagram over here. When we store a distinguished point xb, we also store its index b, and the previous distinguished point encountered, namely xa. So we know the length of the sequence from xa to xb, namely b minus a, and also the length of the sequence from xc to xd, namely d minus c. Suppose that the sequence from xa to xb is k longer than the sequence from xc to xd. We then begin with xa and compute k terms of the sequence up to xa plus k. Now, xa plus k is equidistant from xb as xc is from xd. So beginning with the pair xa plus k and xc, we advance the pair one at a time until we detect that a collision has occurred. The collision then is the previous pair shown as the red dots. Here is pseudocode for the VW collision finding algorithm. The algorithm has two stages. Stage 1, where we detect the collision, and Stage 2, where we find the collision. Stage 1 begins by selecting a random starting point x0. We store x0 and its index in a sorted table. Let LP be the last point stored in the table. Initially, LP is x0. Now, from D from 1, 2, 3, 4, and so on, we'll compute the next term xd of the sequence by hashing the previous term. We then check if the computed term xd is distinguished. If xd is distinguished and already in the table, let's say xd equals xb, where b is less than d, then we go to stage 2. Otherwise, we store the distinguished point xd and its index d in the table, along with the last distinguished point stored. And we update LP to XD. In stage 2, define L1 to be the length of the path from XA to XB, and L2 to be the length of the path from XC to XD. Assume without loss of generality that L1 is at least L2, and let K be their difference. Compute K terms of the sequence, beginning with XA, to get XA plus K. Observe that XA plus K and XC are equidistant from XB, which equals XD. Next, advance XA plus K and XC one at a time to compute the pair XA plus K plus M and XC plus M. Do this until the pair of computed terms are equal, in which case the collision is the previously computed pair. Let's analyze the VW attack. The expected number of hash evaluations in stage 1 is the expected length of the row-shaped figure. That is, until a collision has occurred. This is the square root of n by the birthday paradox. We have to add to this the expected length of the path from when the collision occurs to when the next distinguished point is encountered. And this length is expected to be 1 over theta. And so the expected running time of stage 1 is the square root of n plus 1 over theta. The expected running time of stage 2 is at most twice the length of the longer of the paths from XA to XB and from XC to XD. One can show that the expected length of the longer of the two paths is 1.5 over theta. I won't justify that claim here, but you can read about it in the optional readings on the course webpage. And so the expected number of hash evaluations in stage 2 is at most 3 over theta. Thus, the overall expected running time of the VW attack is the square root of n plus 4 over theta. The dominant term in this expression is the square root of n. The expected storage is the number of points computed times the proportion of points that are stored, namely theta. Each table entry is n bits for XD, n bits for LP, and I'll say n bits for the index D. And so the storage required is roughly theta times the square root of n times 3n bits. Let's revisit the case when n is 128. We can take theta to be 1 over 2 to the 32 by declaring a point to be distinguished if its first 32 bits are 0. Then, the expected time to find a collision using the VW attack is roughly 2 to the 64 hash evaluations. And this is a feasible amount of work. On the other hand, the expected storage is only 192 gigabytes. This storage can be considered to be free because you already have that much storage available on your laptop. In conclusion, the VW attack has the same running time for finding a collision for a 128-bit hash function as the first generic attack. But the space requirements have been reduced from 500 million terabytes to only 192 gigabytes. A very substantial reduction indeed. Even though 2 to the 64 hash evaluations is a feasible amount of work, it's still infeasible to execute on one computer. And so we need to confirm that VW can be effectively parallelized. And indeed it can. Suppose we have M processors available to us. We could run a copy of the VW attack on each of the M processors. Each processor would report distinguished points encountered to a central server, and the central server would check for repeated distinguished points. Note that each processor begins with its own random starting point, and so each processor computes a different sequence. The key point is that each sequence can now collide either with itself or with another sequence as shown here. when two sequences, either from the same processor or from different processors, collide. Then we have a collision of n-bit strings. This collision is detected by the central server because the distinguished point highlighted in the figure will be computed twice, once by processor 3 and once by processor 4. When a collision is detected, then the collision can be found as before using stage 2 of the VW attack. The total number of points that have to be computed by all the m processors before a collision occurs is the square root of n, again by the birthday paradox. But now the points are being computed at m times the rate of when only one processor was used. And so the expected time for a collision to occur is the square root of n divided by m. And, as before, we have 4 over theta for the time to go from collision occurrence to collision detection, and to execute stage 2 of collision finding. The expected storage is unchanged. So we have a factor m speedup in the expected running time of VW. Observe that there is no communication between processors. Observe also that processors only occasionally communicate with the central server. This is when they report distinguished points to the server. And so VW parallelizes very nicely indeed.
Next, we'll present Merkle's method for constructing iterated hash functions, for which collision resistance can be mathematically proven. Examples of iterated hash functions include MD4, MD5, SHA-1, and SHA-256. Iterated hash functions have a checkered history, and collision-finding attacks on MD5 led to the Flame malware. We'll summarize this history in V3d. See you soon!